So we were, looking into various aspects in a previous lecture, right? Various circuits, and few of them were like integrators, differentiators, right? We also looked into few current sources, right? And what changes can be done to them, and we also saw an example, right? We saw using FET, what is the advantage, and using MOSFET, what is the advantage. So the main thing that you have to do here is, you will have to remember the formulas, right? Formula associated with VDS, and also you should remember, the concepts which I told you with regards to generation of drain current, right? Remember, I had drawn a diagram having source, gate, and drain, right? So that should be remembered. And VGS and VDS, these two are important voltages, right? So VGS is basically for making, or to give the voltage between the gate and the source. VDS is between, the drain and the source. So VGS and VDS. So VGS initially turns on the turns on the transistor, and your VDS will actually enable in getting the drain current. Okay, so these were some of the things that we looked into in our previous class, right? So we even looked for a formula, right, with regards to the MOSFET, right, and how or why we should give this +1 volt, right? So it should not go beyond this value, right? It should not go beyond this value. Only then, we can make sure that VDS minimum is maintained. Okay, then we looked into a problem. We saw how to apply, the formula. So the best thing here that we looked into was, having standard, p-channel MOSFET and utilizing those values, right? So this was looked into previously. And we also saw differentiators, right? So how the placement of resistors and capacitors play a very vital role in getting the output, differentiated, where part of the output is actually a differentiated form of input. Okay, and we also saw a few equations. This is one of the major equations. And can someone tell me what is this RC? Yesterday we saw this, right, exclusively. RC. What is it? Yeah, students, what is RC? Do you recall what is RC? So this is nothing but the time constant, right? The value of resistance and capacitance denotes the time constant. Okay, and can someone tell me why we use this RComp? RComp, why we use the resistor RComp? Yeah, students, I need some responses. Because we are transmitting microwave signal, so we need a microwave signal source which will specifically generate microwave signals. Then we need VSW. Yeah. This is for. So we had seen that this resistor here will actually control the effects of bias current, right? Remember, we had IB max. IB max is about 500 nanoamps, right? So this resistor here will actually control whatever effects that can be because of the bias current. Okay, so hence this is needed. So through this resistor, whatever the currents, slowly it is grounded. Okay, fine. So that was one important concept. And we saw few equations, right, where IC is having a standard form. Okay, the current across capacitor C, and how while changing them, from left hand side to right hand side, it gets its minus symbol. So minus is actually referring to a phase shift of 180 degree, right? Then we also saw integrators, right? The only difference was, it was multiplying there, but then here it's at the denominator, and the positions of R and C have changed. And we saw how the waveforms were, right? I give a square wave and then I get a triangular wave, but then in differentiator it was different, right? We were getting the opposite. So we saw a few equations as well, right? Where we saw that the final value is actually minus 1 by R 1 CF and integral of VI into dt. Okay, fine. So R1 CF was playing a very major important role, right, in actually controlling how this integrator functions. So today we will shift our focus, okay, and we'll look into something called log and anti-lock amplifiers. So I think you all have operated the calculators, and you have worked on the log and anti-log functions, right? So the logarithmic function. So now we will just see as to how this log amplifier works. So you can see, this is the circuit here. Okay, so instead of a feedback resistor, we are using a diode D1. So which means we should be very sure. Just a moment. Okay, so log amplifiers, if we have to construct them, right, they will need a diode instead of a resistor. Usually we have a resistor here, right, and integrators and differentiators, they have resistors and capacitors. So here, we are talking of diode, and this diode should be forward bias, right? So you all know that it works in forward bias. But then if it's reverse bias, then it wouldn't function, right? Okay, so figure shows an inverting amplifier with a diode D1 substituted in place of a feedback resistor. So instead of a resistor, what are we using? We are trying to use a diode. Okay, diode D1. Okay, as with a normal inverting amplifier, the op-amp inverting input is held at ground level. So here you can see that the positive terminal is actually grounded. So which means negative terminal is also grounded, and we call it something. There's a specific term for that, students. Can you tell me what it is? We use a specific term for that. It is called
virtual ground.
Yeah, very good. That's right. So since the positive terminal here is at ground potential, right? So the op-amp will make sure that the other terminal also is having the same potential. So that is nothing but called a virtual ground concept. Okay, good. So so we have a virtual ground concept, right? And this is going to be an inverting form, so which means whatever input I'm giving, it's going to be in the inverted fashion. Okay, right. So it is held at ground level because non-inverting terminal is grounded, so the circuit input current is I1 is equal to Vi by R1. So this is my input current, and the voltage V0 is equal to minus Vf. So Vf here is nothing but the forward voltage of this diode. Okay, so you can see here, right? Vf is equal to the diode forward bias voltage. Okay, so whatever voltage is across the diode will actually appear at the output, but then there will be a phase shift, right? 180-degree phase shift. So it's an inverted form. Okay, the typical diode forward characteristics you can see here, right? So it should be maintained below 0.6. So that is one challenge here. Not only using a diode, okay, but then you have to make sure that this diode stays in its proper range. Okay, if you can recall, right, we were talking about the usage of BJT. So while talking about this usage of BJT, we had a condition where, if our outputs are actually less than less than 25 milliamps, then what we are going to do, we are actually going to neglect BJT, which means we are not going to use it, but then we are just going to use the op-amp and the associated resistors and ground and VCC potentials, right? So here now, when I'm using a diode, right, so it becomes important for me to consider its operating voltage, right? So I should make sure that it is below 0.6 volts. Okay, so this diode will have less than or equal to 0.6 volts. So as the voltage increases, right, you can see that the graph is also exponentially increasing. So this is my Vf and this is the If. So beyond 0.6, okay, it's not going to be stable, right? Okay, logarithmic, as long as Vf is less than approximately 0.6. So within 0.6, it's fine. Okay, but greater than 0.6, okay, it's not going to be in a logarithmic fashion. So it's like a log function. Okay, and If is less than 1 milliamp. So not only that, we have to make sure that If is falling below 1 milliamp. So here it increases, okay, goes to 0.6, 0.7, 0.8. At one point, it will reach, let's say this continues, and then it will come to this point. From there, the log function ends. Okay, so with this point here, okay, we might get about 1 million. So I should not go beyond this. I should not go beyond this level, right? But here, it is somewhat increasing when I compare the Vf, right, which is the forward voltage of the diode. So the best sweet spot, okay, that we could actually think of is having it operate in this region. Okay, so that's the best sweet spot, right? So therefore, Vf is dependent on If, and the equation is, so remember this equation, right? So we will need this equation. If is equal to Is e raised to q Vf divided by Kt. You would have seen this, right, where your Is is the diode current. Okay, specifically it is reverse leakage current, and Q is the charge of electron. We have been learning this since our basic semesters, right, which is 1.6 into 10 raised to minus 19 coulombs, right? Then Vf is actually the forward voltage, okay, forward bias voltage, just like we saw here. Output is minus Vf. Then your Boltzmann constant K. So K, all this you can get it in your calculators, the Boltzmann constant and all those, provided you just know the numbers. Of course, behind your calculators you will have it with a constant number. So once you apply that constant, example gravity or Boltzmann constant or charge of an electron, all these will be available. But then it's pretty easier to actually remember than 1.6 and 1.28 into 10 raised to minus 23. Fine. So T is the absolute temperature. So we are looking at the room temperature, ideal room temperature. Okay. So it's about 25-26 degrees centigrade, right? Okay. So this equation we're going to rewrite, okay, and we're going to retain only VF, which is the forward voltage, and we're going to take the other sections, okay. We're going to interchange the left hand side and right hand side. So doing that, what is going to happen is, I'm going to get an equation where I'm going to have the ln function. Okay, so this is where the logarithmic function comes into picture, right? So Vf is equal to, I have kt here, okay, kt by q, okay, and then if, so is, so this is comes down, if by is, then Vf is remaining here. So if I have to take this section, then I have to take ln of if by is. Right. So this equation is important. You need to remember this, right? Vf is actually kt by q. So k is your Boltzmann constant, T is the temperature, right? And q becomes your charge of an electron, right? Okay. So now we have this equation here, okay, which is 7.6. Okay, it's actually referring to this equation, the forward voltage, right, wherein it's dependent on k, t, q, if and is. So the major player here is going to be the diode. Okay, diodes, forward current, leakage current. So this becomes the forward current, this becomes the leakage current. Okay, and the associated environment. So environment is like temperature and the other things. So here in this equation, if, okay, is the diode forward current, which is also the input current I1, and I1, we have seen that if you see here I1, okay, it's actually dependent on Vi and R1, right? So I is nothing but Vi by R1. Okay. Right. So, so you can see that, we are taking a constant of about 25 degrees centigrades, right? So 25, 26, is taken to be normal, room temperature, right? Okay. So, you can see that, we are going to consider this 25 to 26 degrees centigrades, right? And when I do a KT by Q, so approximately I'll be getting 25 millivolts. Okay, so you can consider this as a constant. As a whole, probably, even without you calculating, okay, if you can just remember this value, which is KT by Q. Okay, so that's approximately about 25 milliamps, right? Okay, so sorry, millivolts. The circuit output voltage V0, as we have seen, is actually the negative form of Vf, right? So that is because it is connected here to the inverting terminal, right? So V0 is equal to minus Vf. So if we have to rewrite this equation, right, if we have to substitute them, okay, so we will actually get, so since V0 is equal to minus Vf, so I substitute Vf by V0, right, and I take the minus, and KT by Q is 25 milli, so 25 milli into ln, okay, and If, okay, the current which is dependent on the forward current, right, which is dependent on Vi and R1, and Is is anyway going to be multiplied because it's in the denominator, right? So we have a revamped equation here, right? So which seems to be much you know, what to say, much refined, okay, because we have few numbers here and we know what is IF, right? So IF is VI by IS, right? And KT by Q, anyway, we have substituted the values. And now, okay, instead of having VF, we know that our output voltage is actually having a logarithmic function. Okay, fine. So this equation is actually showing us that the circuit output voltage has a logarithmic relationship to the input voltage, right? So you can see that, you know, the output is here, okay, the output is here, and you have the input here. So output and input both are related. In what form? They are related with the help of this logarithmic function. Also, because of the op-amp inversion, right? The inversion, as you all know, it's happening because of this negative terminal. Because of the op-amp inversion, the output is a negative quantity with the input being positive. So here you have negative, right? So here you have negative form, but then VI is going to be in its positive form. Okay, right. So the diode connected has shown the circuit cannot accept negative input voltages. Can you tell me why we cannot accept negative input voltages? Why it cannot accept negative input voltages? If in case there is a negative input voltage, then what happens? Yeah, students, what happens if there is a negative input voltage given? Can we actually bias the diode? Is it possible? So that actually reverse biases, correct? So that actually reverse biases, right? So because of which I'm not going to have a negative potential given, okay, because I'm interested in looking at, you know, making the diode be in forward biased condition. Okay, so that's the whole idea. Okay, so the diode must be reversed to deal with negative inputs, and when reversed, it cannot accept positive voltages, right? So this is important here. If in case, you know, we are giving a negative potential, okay, so with the help of diode, I will be able to remove it, right? I'll be able to block them. That is because of the property that, you know, diodes, okay, do not accept or do not function in reverse biased condition, right? So is that clear, students? Can we make any changes to this circuit? Instead of diode, can we put something else and get the same functionality? Is it possible? Yeah, can we do that? Okay, so we will look into that, right, as to how and what changes. So one thing you should understand, we're going to give a positive potential here. So this is going to be forward biased, and making sure that it's between 0.6 volts and 1 milliamp, so that I get the proper, you know, logarithmic functionality here. So once I have this proper logarithmic value, right, then its name holds good, right? Log amplifier. So and then you can remember this equation here, right? So this is important. Or if you can just remember this VF, okay, that's also going to be fine, because anyway you can substitute the value of VF with V0, okay, which is going to be minus V0 is equal to minus VF, right? So that is one thing. And yeah, either one of them, if you remember, it's fine. Anyway, ultimately you can substitute this value also here, which is 25 millivolts, right? So it can be substituted. And two things, right? Two things keep in mind. You're substituting V0's value, and you're substituting KT by Q's value. So both you substitute, you get a much refined equation, right? And this is what we're going to get. Now you're seeing here that Vi is a positive potential, right? We're not giving a negative potential. The reason being, the diode, right? The reason being the diode, right? Okay. So suppose I give a negative, then this is going to be reverse biased. So which means there is not going to be any conduction. And if there is no conduction, then I am not expecting any outputs from the diode. So which means I am not getting any output. V0 is equal to V0 is equal to 0 because it's reverse bias. There is no feedback, right? So I cannot expect anything from my op-amp, right? So have you all understood this? Can we move on to the next concept? Any doubts here, students?
No, sir.
Okay. Right. So let us solve a simple problem here. Okay. And we will get to know how to, actually find out the values. Okay. So we have a log amplifier circuit. Okay. So which means we're going to use the same circuit here. Okay. And this has R1 is equal to 47 kilo ohms, and the diode has IS is equal to 25 nanoamps. Calculate the output voltage when input is 1 volt. So Vi is there, IS is there, R1 is there, right? So we need to calculate V0. So first we will go with the formula, right? V0 is equal to minus 25 millivolt, right, into ln of, okay, and I put this formula, I substitute the values, and Vi I have it as 1 volt, right? So I just substitute it, I bring it down, right? So yeah, and then IS I have the value as 25, right? So 25 is brought down and R1 is 47. Very simple problem, isn't it? So can we just calculate them and find out if it's correct? Take out your calculators and help me verify if the value is proper. So first what you can do is you can probably calculate the denominator, right? 25 nano into 47K you can do, and probably you can take an inverse of that, right? And calculate if we are getting a proper value. 25 nano into 47K. Okay, so you can take ln of that value and you can multiply it with 25 milli, right? So are we getting the same value? Either you can take the numerator 1 divided by, or as I mentioned, first you take this denominator, okay, you will have a value, take an inverse of that, and of course you don't have to multiply with the numerator because it's just 1. To that value you take ln, and to that value you multiply with minus 25 milli. So are we getting this value? Yes, no?
Getting, sir.
Okay, that's good. So I think we must be getting about 168.662, isn't it? So
Yes, sir.
so we can round it off 0.662 to to the next higher value. So we'll get about 169 minus 169 and 10 raised to minus 3. So yeah, that's going to be milli. Fine. So this value is correct. So ultimately, you should remember the formula, right? Uh, and most of the things will actually be given in the questions, right? So based on the question, you will actually get to know that these parameters are in your formula. In fact, question gives you a lot of clues, right? So you know that R1 is supposed to be in your formula. IS is supposed to be in your formula, right? And the input voltage is also supposed to be in your formula, right? So just that you need to have a negative KT by Q and then log, right? So pretty simple problems, right? So data can be changed and given differently for your exams or semesters, semester internal exams. Okay. Okay, so now that we have learned how to solve a problem or how to find out the output voltages, right? And how to maintain the values for diode, not making it go beyond 1 milli and not making it go beyond 0.6. Okay, so all this is actually possible with your input voltage, right? Input voltage and the kind of resistance that you are actually connecting here at the input side, right? So ultimately we can control and make sure that we have a log type of waveform. So ultimately we are looking at the applications of op-amp. So which means we can configure it as an integrator, we can configure it as a differentiator, okay, and we can get different waveforms when connected in different formats, and then we can also make sure that we get log functions out of it, anti-log functions out of it, right? So that's why this op-amp is called a wonder circuit, right? So once this came in the field of electronics, right, so people started exploring its possibilities, limitless possibilities, and trying to get the best out of it. Now, the other thing, that impresses engineers and scientists is about its bandwidth, okay, its gain, and the input impedance, output impedance, right? So all this actually impresses. So slight modifications done to the lumped circuits connected, like resistors or capacitors or diodes or anything for that matter, right? So you can actually alter its properties and you can make sure that it works in a different fashion, right? Okay, so now what we are going to do is we are going to have the same circuitry, right? But then instead of the diode, right, we're going to replace it with a BJT, right? So as you all know, BJTs are also as good as MOSFETs, okay, with current carrying capabilities. So we're going to include a BJT here and remove diode D1, and we're going to see how it's going to function, right? So this resistor is remaining the same, plus VCC minus V, and then you have the output voltage V0 and input voltage Vi. So all these are going to remain the same. Current I1 gets generated, it passes on here and then gets into the BJT, okay, and exits and comes to the output terminal V0, right? So a BJT, can also be used as a log amplifier. So which means we are looking at, the logarithmic function to happen. So which means our output waveform, okay, our output waveform should actually go in a log fashion. So here I'm going to have, voltages, right? Voltage levels. And here I'm going to have current. So you can call this as a VI characteristics of a diode. Okay, so the only thing that we have to make sure is that it remains in its limits. Okay, so the limits are about 0.6, right? 0.6 here, and I have to make sure that there is going to be about 1, right, about 1 millivolt here, milliamps here, right? So if we are able to maintain these two, parameters, okay, 0.6 and this one, then only we'll be successful in having a diode. So in order to eliminate these kind of conditions where I do not want to have a 0.6, I do not want to have 1 milliamp, then that's when my focus shifts to having a BJT. Okay, so let us see how this BJT actually helps us in getting the functionality done. Functionality means having this kind of log waveform. How is it possible? Okay, fine. So a BJT may be used in log amplifier, okay, instead of a diode. And in this case, both the collector and base terminals of the transistor are held at ground level. So collector and the emitter, right? So here, sorry, the base, right? So the collector and the base terminals, right? Collector and base terminals, right? So base is held at constant ground potential, okay, and you have this also held at ground potential, okay, just because of the virtual ground concept that we studied, right? This plus is actually connected to the ground, so which means you can analyze that this op-amp will actually make sure that this is also in ground potential, right? So you can understand that even here, okay, even here it is at ground potential. So this is nothing but called your virtual ground concept, right? So I have two terminals here kept at almost virtual ground concept, right? So this is going to be my ground and this is going to be virtual ground, okay, are held at ground level. The base emitter junction is forward biased, so you have this base emitter, right? So this is forward biased, so between the base and the emitter, okay, and the device behaves as a diode. So this is a specialty here. Now, as you all know, okay, your transistor, okay, will have junctions, right? Junctions like P, N, and P. Okay, so I am going to explore the possibility of this. So wherein few sections, few portion of your transistor is made up of P and then N and then P, right? So in order to have a diode, okay, in order to have a diode, I just need two junctions, right, which is P and N. So if I can explore this P and N junction here, okay, then it is as good as having a diode. So it's like having a transistor but then making it function like a diode. Is that clear, students? Any doubts here? Any doubts here as to how we are actually making this transistor into a diode? We are exploring the options of the junctions. Okay, is that fine?
Yes, sir.
Right. So once we have that, okay, once we put it in, and remember, we are always looking at forward biasing alone. Okay. Now, why are we looking at forward biasing? As I told you previously, it doesn't function in reverse bias condition, isn't it? So it's as good as cutting off the feedback network, as good as having no circuit or no diode or no transistor connected here. Okay, so the device behaves as a diode with voltage drop VBE. So you can imagine the voltage between the base and emitter. Okay, so this is here in ground potential and the emitter. So we might be able to apply the equation, okay, to BJT circuit as well. And this IS, okay, is actually representing, you remember this IS was actually the leakage current of the diode, right? So this can be replaced with the base emitter junction, okay, reverse leakage current. Now this is again a different concept, okay, where there can be a slight leakage happening between the base terminal and the emitter terminal. So in short, we call it as IEBO. Okay, so the leakage current that happens between base and emitter, okay, and that is in the reverse form. Okay, so reverse current. So in this way, we can actually replace diode, and we can utilize a BJT and make it function like a diode. Okay, so once it functions like a diode, then ultimately I can make sure that this is this waveform is met. So I'm going to get a logarithmic waveform, right? So any doubts here, students? Is it all fine?
Fine, sir.
Yeah, okay.